So E part 1, silver sulfide Ag2SO3 solid is a sparingly soluble salt in water. So the sparingly soluble are the ones which usually dissolve in a smaller amount. Give an expression for the solubility product for 2SO3. So if you write its dissociation equations, it is H2Ag2SO3 dissolves slightly to form 2 moles of Ag positive and 1 mole of SO32 negative, right? So if I'll make the KSP equation, if I got this from this, I can easily make the KSP expression. So it would be square of the concentration of Ag positive ions times concentration of sulfide ions. Is this clear to all of you? Okay. Now, in the next part, they are saying calculate the equilibrium concentration of Ag positive in a saturated solution of silver sulfide at 298 Kelvin. So it means we have to calculate the concentration of Ag positive ions, right? So let's assume that the concentration of Ag positive ions is X. So if the concentration of Ag positive ions is X, so on the basis of equation, no, 1 minute. If you see over here that there are 2 moles of Ag positive and 1 mole of sulfide ion, so we will consider that X as a X, and if it is X, then it would be 2X. Is this understandable? So now I am going to put it in a KSP expression. So we got the KSP value, which is 1.50 exponent minus 14 is equals to, instead of concentration of silver ion, I'm going to write 2x square times concentration of sulfide ion, which is X. Till here, is this clear to all of you? Yes, is this clear? Okay. Now, then it would become 1.50 exponent minus 14 is equals to, it is going to become 4x square, and 4x square times x would be 4x cubed, right? If I'm going to find the concentration of x, if I'm going to find the value of x, so x would be equals to cube root 1.50 exponent minus 14 over 4. No, because see, it's a 2x. So when we take the square of 2x, it becomes 4x square, right? And 4x square times x would be 4x cube. Okay, so we got this. Can anyone tell me the value, please? Okay. Can anyone check it? And Shrey, you can cross check it. Is it 6.123 exponent minus 8? You have to take the cube root, right? Yes, Shrey, please recheck it. I'm asked, yes, what you want to be repeated. I'm just saying that calculate this and tell me. Okay, Ali Asad is getting 1.55 exponent minus 5. Yes, Sohaib and Shreya are getting the same thing. Yes, Nuria, what you didn't understand? So x is equals to 1.55 exponent minus 5. And it's a mole per dm cube. Yes. Okay. If you look at their mole ratio, it's 1 is to 2, right? So if I assume this x, then it would be 2x. Now, if I put the values over here, because we don't know, so the sulfate ion would be x and silver ion would be 2x, but in the formula it's the square, so we keep the square. So when we solve it, it will become 4x cube. Now if I have to find the x, so it's a cube, so here it will become a cube root, and the 4 is multiplied by x, so when it moves over here, it is going to be divided. So when we solve this, we will get this value. So these are the moles of X. So it means this is the concentration of sulfide, and they are asking you to find the concentration of silver. So this concentration of silver would be twice of X. So what I'm going to do, I'm going to multiply it with the 2. So on multiplying it with the 2, I'm going to get the concentration of silver ions. Is this understandable to all of you? Can anyone calculate this and tell me the answer, please? Okay. Thank you, Shrey. 3.11 exponent minus 5 mole per dm cube. Okay. Now, the standard enthalpy change of solution of silver nitrate solid in water is plus 22.6 kilojoule per mole. Okay. Suggest how the feasibility of dissolving of silver nitrate in water changes with the temperature. Okay. So it's an enthalpy change of a solution, right? So it means when silver nitrate gets dissolved and turns into aqueous solution, its enthalpy change of solution is positive to 2.6, right? Is this clear to all of you? Okay. Now, if you look at this equation, can any one of you tell me the entropy change? Would it be positive or a negative? Yes, the change in entropy, it's a positive. Very good, Mariam, because the solid turning into aqueous sign, so it is going to be positive. Now, if you recall the feasibility expression, the Gibbs free energy equation, it is enthalpy. Gibbs free energy is equals to delta H minus T delta S, right? And what they are is saying when the with the temperature. So we have to explain with the temperature the feasibility. Okay. Now, this value, right? And this value is positive. So as a result, this whole thing becomes negative. So there is a one value positive and one value is negative. So what will happen if delta H is greater than minus T delta S? Then the answer is positive. And if the answer is positive, then it means that it's non-feasible. Is this understandable? If this is the case. Yes, from what you want to be repeated, Moaris? Yes, Morris, what you want to be repeated? That this is a solid and this is a aqueous. So aqueous have a more, irregularness. If it's a more irregularity over here, more randomness in it, so the entropy change would be positive. Now, this is the equation of that gives free energy from which we can find the feasibility. So if you see delta H is positive, right? And entropy change is positive. But here the sign is negative, which makes this whole term a negative. So we have a one term positive and one term negative, right? So if this is the case, if the delta H has a greater value than this one, so the answer would be positive, and it means that the reaction is non-feasible. Is this clear to all of you? And if yes, still here, is this clear? Okay. Now, if this is the case that delta H is gets smaller than minus T delta S, so we get the answer in the negative and the reaction becomes feasible. Okay. Now see, this value is going to be constant. The enthalpy change is not changed, and the change in randomness is also going to be constant. So how this happens that the T delta S becomes, greater than delta H? It is only possible due to the temperature is increased. What happens to the temperature? The temperature increased. So see, that's what I'm going to explain it over here, that how the feasibility of dissolving silver nitrate in water changes with the temperature. So I can say that feasibility increases with the increase in temperature. As at higher temperature minus T delta S gets more negative, or you can say that minus T delta S gets bigger than delta H, hence gives free energy gets negative, and if free energy is negative, it means reaction is feasible. Is this clear to all of you? Now, yes, I hope it's clear to all of you. Now, question number 4A. In an aqueous solution, iron 3 iron 3 iodide ion as shown. A series of experiments is carried out using different concentration of iron 3 positive ions and iodide ion as shown. Explain what is meant by the overall order of a reaction. So, if you have to write the overall order of a reaction, you can write uh, it is the sum of the power to which the, because the overall order is identified by summing up the orders. Whenever they ask you to, Mariam, whenever they ask you to find the feasibility and they are giving you the enthalpy change and you can easily predict its entropy change, you always use that Gibbs free energy. That the Gibbs free, that the delta G expression, that delta G expression, that delta G is equals to delta H minus T delta S. You always use that one. Okay. So it is the sum of the power to which the concentration of the reactants based in rate equation. Use the data in table 4.1 to deduce the order of a reaction with respect to iron 2 positive and with respect to iodide. Okay. So I can use experiment 1 and 2 because these two are constant. And if you see, the concentration of iron is raised by 3 times, isn't it? So if I know the factor by which the rate is changed, I will able to identify the order with respect to iron 3 positive. Okay, Mariam, is your queries cleared yet or not? Okay, so can anyone tell me by which factor the concentration, the rate gets changed? So for that you have to divide 7.92 exponent minus 4, the greater value with the smaller value 2.64 exponent minus 4. So is it 3? Okay, Shrik. So we are getting the factor by which the concentration of iron 3 positive is changed and the rate is changed is same. So it means it's a first order with respect to iron 2 positive ions. So I will write that from experiment 1 and 2, the concentration of iron 3 positive and rate both are changed by 3 times. Hence, its first order with respect to the concentration of iron 3 positive ions. Is this clear to all of you? No, if the what you were saying, if the rate would be doubled, it's doubled when the concentration gets doubled. If the concentration is increases by 4 times and the rate is also gets increased by 4 times, so it's first order. So the first order means by which factor the concentration is raised, the rate must be raised with the same factor. That's what the first order is. Is this clear to all of you? Now the other one is a little complicated, so I want you guys to be really focused to understand the next thing. Because if you see, if we compare experiment 1 and 3, or if we compare experiment 2 and 3, in both the cases, both the concentration of both the reactants are getting changed. So I want everyone to be very focused, okay? Okay. So if I try with the experiment one, so I'm clearly observing that the rate is going to be increased by 2. The concentration is increased by 2, isn't it? Is this one is clear to all of you? So we know that the order with respect to iron is 1. So it means that due to iron, the concentration, the rate is also going to be times 2. But if you see over here, if you look at this thing, okay, I am using a different color, so it will be identifiable to you guys that the concentration of iodide is also changed by 2. It's also get doubled. Is this clear? So can anyone identify that by which factor this changes? These two are changing by which factor? What is the change over here? 10 exponent minus 3 divided by 2.64 exponent minus 3. Okay, it's minus 4. Yeah, can anyone tell me the value over here? It's 8. Thank you, Shri. So see, I just put a 2 over here, and why I did so, just understand this thing. First, we used experiment 1 and 2, and from experiment 1 and 2, why we took these two? Because we have seen that there is no change in the concentration of iodide. The concentration of iodide is constant. So we have seen that the concentration of iron is increased by the factor of 3 in experiment 2. So when we observe the change in the rate, so we have seen that the concentration, as the concentration is increased by the factor of 3, the rate is also increased by the factor of 3, and from this we can conclude this that it's the first order with respect to iron 3 positive ion. Is this clear to all of you? Okay. Now see this. Now what I did, okay. So now if you see in experiment 1 and experiment 3, the concentration of iron is increased by the factor of 2, right? So we will be sure because from experiment 1 and 2, we have concluded that the order with respect to iron is 2. So the rate over here is also going to be increased by 2 due to the iron. But when we identified the factor by which the rate is changed, so the rate is actually changed by the factor of it. So it means rate is also changing over here due to 4, due to the factor of 4. And this factor of 4 is due to iodide because we knew the order with respect to iron. So we are sure that if the concentration of iron is doubled, the rate is also going to be doubled. But as the rate is going to be increased by the factor of 8, so it clearly means that the increase in rate, that is by the factor of 4, is due to the concentration, doubling the concentration of iodide. So if you see, it's get doubled, but the rate is actually gets square of that. So it means it's second order with respect to iodide. Is this understandable? So I'm going to write over here that uh, from experiment 1 and 3, the concentration of iron is raised by 2 and the concentration of iodide is also raised by 2, but rate is raised by 8. Hence, its second order with respect to the concentration of iodide. No, if iodide was not doubled, so the rate would only be gets doubled. So the rate is only increased by this factor because we concluded from experiment 1 and 2, it's first order with respect to iron, and the concentration of iron is increased by 2. So if it is not changed, if it was the same, so the rate is also gets doubled over here. Yes, is this clear to all of you? Use your answer to A2 to construct the rate equation for this reaction. Okay. So what we know, okay, in rate equation, rate is equals to rate constant K times concentration of iron 3 positive, which is raised to the power 1 because it's first order, times square of the concentration of iodide because it's second order. So that's what the rate equation would be. Now, use your answer to A3 and the data from experiment 1 to calculate the rate constant K for this reaction and include units. So, okay. So if you make the equation for K is equals to rate over concentration of iron 3 positive times concentration of iodide square. So if I put the values from experiment 1, they have told you to do it from the experiment 1. No, Maham. See over here, it is increased by 2 and it is increased by 4. So it means it's second order. Okay, because it is just getting double and it is getting quadruple, it is getting 4 times. So it's, yeah, because it is doubling than this one. That's why it's a second order. If this and this change would be same, then it's a first order. Okay, so now we need to put the values over here. That K is equals to, for first order, the rate is 2.64 exponent minus 4 divided by concentration of iron is 0.04 times concentration of iodide is 0.02 and it's squared. So can anyone calculate and tell me the answer? The unit of rate is mole per dm cube per second. And over here we get the mole per dm cube. And over here we will get the mole per dm cube whole square. So these two would be cancelled out, and when the mole per dm cube whole square goes to the numerator, it will become mole inverse square dm6 and second inverse. So yeah, it's 16.5. Is this clear to all of you? Describe qualitatively the effect of an increase in temperature on the rate constant and the rate of this reaction. So if you see, this is the rate equation. Now let's take the example of experiment 1. This is the rate, and right now this reaction is happening at 25 degrees Celsius. Now, if instead of 25 degrees Celsius, if this reaction would occur at, let's suppose, 100 degrees Celsius, would the rate would be the same? Yes, very good, Maham. Or rate would increase at a higher temperature. Yes, at a higher temperature, what happens to the rate? Will rate increase or it stays the same? It will increase. But what happens to the concentrations? Do the concentration increase or they stays constant? They stays constant. So see over here, if you look at the equation, these two values are constant, but at 100 degrees Celsius, the value of rate would be higher. So it clearly means that the K will increase. Is this clear to all of you? On rate constant and rate of reaction, so see, that's what we are going to do. Both rate and rate constant increases. Now B. In aqueous solution, iodide ions react with acidified hydrogen peroxide as shown. Okay. The initial rate of a reaction is found to be first order with respect to iodide, first order with respect to H2O2, and zero order with respect to hydrogen ions. Shows a possible four-step mechanism for this reaction. Okay. So it means if I may try to make the rate equation, so the rate equation would be rate is equals to K, concentration of iodide ions times concentration of H2O2 ions, that's it. Suggest which of the steps 1, 2, or 3, or 4 in this mechanism is the rate determining step. So the rate determining step would involve iodide and H2O2, but do not going to involve hydrogen because the with respect to hydrogen it's 0. So then which will be the rate determining step? Yes, who can tell me the answer? Very good. And see, there is a concentration, there is the powers are 1, the order is first. So the moles in the rate determining step, uh, the moles of H2O2 and I negative would be 1 and 1 only. So I'm going to write 1 that it's step 1 because in it there is 1 mole of H2O2 and 1 mole of I negative. Is this clear to all of you? Okay. Now two part. Identify a step in figure 4.1 that involves a redox reaction. So redox reaction involves the change in oxidation number. So if you look over here, here the oxidation number of hydrogen oxygen is -1 because in H2O2 it's hydrogen peroxide, and whenever the peroxide term is used in peroxide, oxygen always has a oxidation number of -1. And over here, if I'll work on it, for example, the net charge is 0. So it's -1 times 2, and it's +1 times 2 makes it 0. And here the net charge is -1. Iodide is +1 and oxygen is -2. So it's a redox reaction. That because if you see I negative changes to -1 to +1, and oxygen changes to -1 to -2. So step one, and they okay involve the redox reaction as oxygen. We can write oxidation number of oxygen -1 to sorry -2, and oxidation number of -1 to +1. Is this clear to all of you? Now, so what is the role of HiO negative in this mechanism? Okay. So if you see this I negative, and here it is becoming 0. So it means it's undergoing oxidation. So if it's undergoing oxidation, so it is going to be a oxidizing agent. So the role of HI would be HIO is an oxidizing agent as it oxidizes iodide to iodine. Is this clear? Okay. Now, question number 5. Methyl benzene can undergo different reactions as shown in figure 5.1. Okay. So reaction 1 is the reaction with the hydrogen and platinum. So it's an electrophilic addition. And in this reaction, what happens? That it destroys the firing system, and we get a cycloalkane instead of a benzene. When we react with the bromine and a UV light, so it would substitute the hydrogen from the alkyl side chain, and there is no substitution on the benzene. Okay. When we react with the bromine with the FeBr3, which is a catalyst for the electrophilic substitution, so we get a two products. One, that methyl group substitutes the next group at 2 and 4. So this one and this one. Yeah, here it's a free radical substitution. Here it's a electrophilic addition, and here it's a electrophilic substitution. Further, as the hydrogen are being added, so it is also considered as a reduction or hydrogenation. Okay. Now, complete table 5.1, reaction 1. Okay. So as we have decided that it's a reduction, and reaction 2, they have asked me the mechanism for reaction 2. So its mechanism is free radical substitution for reaction 2, because see, on a side chain it's getting substituted. Yeah. Is this clear to all of you? Okay. Now, B part. When methyl benzene reacts with an electrophile, a substitution reaction occurs. No addition reaction takes place under these conditions. Explain why no addition reactions takes place. Guys, please give me a minute. Yes, Maham, instead of reduction, you can write hydrogenation over here as well because hydrogens are being added. Okay. So why no addition reaction takes place? It is because, as we have discussed, that the substitution, it is delocalized by the pi bonding system or the pi electrons. The substitution product form is easily gets stable due to delocalization. See, the electrons are actually delocalizing, they are moving around. So these are not going to be, gets unstable easily. Till here, is this clear to all of you? Okay. Now, okay, see. The reaction of a methyl benzene with thionyl bromide in the presence of an iron 3 bromide catalyst is shown in figure 5.2. Okay, here we have a equation. The mechanism of this reaction is similar to that of bromination of benzene. So see, they have told you that the reaction is the mechanism is exactly the similar. The first step of mechanism generates SOBr positive electrophile as shown. The reaction of the methyl benzene with SOBr positive ion is shown in figure 5.3. Okay, over here. Complete the mechanism in figure 5.3. Include all relevant curly arrows and charges. Okay. Draw the structure of the organic intermediate. Okay. So let's start with this. What will happen? That a curly arrow from here, and when this curly arrow gets over here, it's a methyl benzene, right? So methyl benzene is going to substitute the next group on second and fourth carbon. So I will, and here, if you see, it's on the second carbon. So I'm going to put it on the second carbon. S double bond O Br. And as we know that each carbon is bonded with one hydrogen. So I'll show that hydrogen as well. And here the pi system is disturbed for us sometimes. So it would be like this. Then I will make one curly arrow from here onwards over there. And as a result, we will get this, and hydrogen ion gets substituted over here. Okay. Hydrogen ion gets replaced. Hydrogen ions gets replaced. Okay. So the hydrogen ion that gets removed from here will be written over here. Is this clear to all of you? Okay. Now, the reaction shown in figure 5.2 produces a small amount of a byproduct P with the molecular formula of this. So it is the structure of a byproduct. Okay, so see, it's very important how you will figure out this product. If you see how many carbons this has, isn't it? It has a 7 carbon. And if you count the hydrogens, if I'm not wrong, 1, 2, 3, 4, 4 and 3. It has a 7 hydrogen and SOBr. Is this the formula of the product? Right? So the one product we are getting over here is C7H7 SOBr. And if you see this, so isn't it this possible that when two of these molecules react, so we will get C14, H14, SO, and Br get substituted. So it means that the byproduct would be two benzene rings or two methyl benzene. One is this one, and one is this one. And over here, sulfur and like this. Is this clear to all of you? If any one of you has any confusion, you can ask. Okay, Maria. How you are going to know that S is in the middle? If you see over here, if you open its structure, isn't it like this? Just give me a minute, please, everyone. Okay. Now, so if you see this product, one of the bromine gets substituted, and over here we get the high benzene ring. Is this understandable to all of you? So isn't it the possibility that if one of the bromine gets substituted, then the other bromine gets substituted, and here we are going to get the second benzene ring as well? Yes, Mariam, now did you understand? Okay. Now, acyl bromides can be synthesized by the reaction of carboxylic acid with the SOBr2. Isn't it like this? When we react SOCl2, we get acyl chlorides. That is the part of the syllabus. So instead of acyl chloride, they have used the term acyl bromide. This is similar reaction to the synthesis of acyl chlorides using SOCl2. See, that's what they have asked. They have stated. Give an equation for the reaction between ethanoic acid and SOBr2. Ethanoic acid means the carboxylic acid having 2 carbon atoms, so it would be like this only. And then it is reacting with SOBr2. So if you recall this reaction with the SOCl2, what we get, the OH gets substituted and we get the Cl over there. So now instead of Cl, Br gets substituted, Br substitute the OH, and then sulfur dioxide gas is formed in this reaction, and hydrogen bromide, because when we use SOCl2, we get HCl. So here we get HBr. Is this clear to all of you? Okay. Now, suggest the relative ease of hydrolysis of acyl bromides, RCOBr, acyl chloride, and alkyl chloride. Explain your answer. So, acyl bromide is RC double bond OBr. Then we have acyl chloride RC double bond OCl. And then we have a alkyl chloride RCl. So among these, which one is going to be hydrolyzed more easily, most easily, or most readily? Yes. So this is what we have discussed in the syllabus, that among these, this one is going to be, dissociate more readily and hydrolyze more readily, isn't it? But if we compare these two, as chlorine, the bromide ion atom is very bigger, so the bond length increases, and the bond length increases, making it weak. Yes, Maham, very good. So acyl bromide is the one which is easiest to hydrolyze. Acyl bromide. And then acyl chloride. And then alkyl chloride. Okay. Now we have to explain the reason, right? So in acyl bromide, the carbon bromine bond is very weak as compared with carbon chlorine bond of acyl chloride and alkyl chloride. Is this statement is clear? Then we will write that acyl chloride hydrolyzes or hydrolyzed more readily than alkyl chloride because CCl bond is weaker than in alkyl chloride. It's the CCl bond of acyl chloride is weaker as attached to C double bond O, which makes it weaker. Okay, then alkyl chloride is very difficult to hydrolyze because alkyl groups causes positive inductive effect. Is this understandable to all of you? So carbon chlorine bonds gets stronger. If any one of you has any query till here, please ask. Okay, yeah. I wanted to ask if we do a class tomorrow at 8 p.m. PST. Is this fine with all of you? Yes, as if you are not available at 8 p.m. Okay, yes, you are available. Why you said no, sir? Okay, so I will update in the group. Probably I'll. Which query you are not clear? Okay, so I'll update in the group, but probably tomorrow we are going to have a class at 8 p.m. PST. No, Alina, bromine is less electronegative. So how can bromine pulls the electron? It has a bigger size, so its electronegativity is lower. Okay, so see you everyone in the next class. Okay, take care. Allah Hafiz. Goodbye.